Now, we're going to start sharing the screen here. Good. Today is November 14th. Monday. And what we have so far here, you go. Okay, so 1. I corrected the reports for labs 2 and 3 and uploaded the correction to your group folder. Okay, that's one thing. I also adjusted the grade of exam 2 in Canvas. Just checking there. And I added the points for those questions that had problems. Okay. So you should have a better grade now. What else? Let's see here. No, it's not this one. I want this one. Okay. So here go. Here you go. We have a new homework, chapter 9 on rotational dynamics that I posted there in the Wiley Plus. Okay, new homework. New homework posted on Wiley Plus. That's homework 10. Homework 10, chapter 9. Posted on Wiley Plus. So that's what I have here. And okay, so and we finished chapter 9. We finished chapter 9 on rotational dynamics. And what I would like to do, let's see, let's take a look at the syllabus here. So we have, we have 10 and 11. Well, I'm gonna try to cover chapters 10 and 11 today. Okay, that's gonna be fluids and simple harmonic motion. Okay, so let us start with simple harmonic motion. Okay, let's follow what the book has for us, the way the book is organized. Let's take a look there at the book. Right in here. Okay, chapter 10, simple harmonic motion and elasticity. We're not going to cover everything here, okay? Well, we're only going to cover 10.1, 10.2, 10.3, and 10.4. Everything else I consider it to be advanced, more advanced stuff, okay, for material for more advanced course. And on the top of that, we don't have time to cover everything. So let's stick to 10.1, 10.2, 3, and 4. Okay, so here we go. We will start chapter. We will start chapter 10 on simple harmonic motion, SHM, simple harmonic motion. Okay, so why do we study simple harmonic motion? Okay, there's a reason why we study simple harmonic motion. We study SHM because it has several important applications in real life. Okay? Several important applications. The most obvious one, okay? Comma, the most obvious one being a way to keep time. That's the most obvious one. We can use simple harmonic motion to build timepieces, okay? We can use SHM to build very accurate and precise timepieces. And that was a huge, when people started using simple harmonic motion to keep time, it was a huge advance in the science of timekeeping at the time, okay? Believe me, it was a quantum leap when people start to use simple harmonic motion just to keep time. And the story is fantastic, okay? It's an incredible story on how they managed, how we, the society managed to use simple harmonic motion to keep time, okay? This story, the story of timekeeping using SHM starts with Galileo Galilei. Galileo Galilei, one of the giants of physics, okay? This guy, did his work back 500 years ago, and we still remember him, okay? But remember, that's just one thing that's just one application, but there are more applications on simple harmonic motion, okay? This one is just one of them. And the story goes, okay? The story goes that Galileo Galilei was at the church, attending the church, and he notes it. When he notes it, that the chandeliers of the church was oscillating, right? Was oscillating around their vertical axis. Oscillating around the vertical direction. And just by looking at that, he starts thinking. And just by looking at that, he started thinking if he could use this type of motion to build a timekeeping device. That's think about that. We had devices like that would oscillate according to the wind that would blow, right? That doesn't have to be a chandelier. Could have been only any device that had a string and a mass attached to the end of the string, right? And nobody thought about using a device like that, which is we call a pendulum, for timekeeping applications. It took someone special, very special, right, called Galileo Galilei to start thinking about it. And we have this story of his in Wikipedia. Let's take a look there. Let's see, Galileo. Galilei, and it's in the Wikipedia. They have a very nice explanation. Let's see if that's the right place here. Okay, that's him, Galileo Galilei. You can see that, right? just confirm with me that you can see this. Yeah, you can see that. And this is a type of guy that made huge contributions to science, not just timekeeping, but he was, he was able to use a telescope to observe several celestial bodies that, he was in the center of the revolution in physics at his time. He was born in 1564 and died in 1642, right? He lived during the ages of navigation, the age of discovery. He lived during the ages of discovery when the European countries, mainly Portugal, Spain, England, the Dutch, right, were navigating around the world and discovering new lands and settling them. The Portuguese was the first one. Okay, the Portuguese were the first one to do that. But he was living during that time. Okay, he was this, Galileo Galilei today is considered an astronomer, physicist, and engineer. Okay, engineer as well, not just a physicist, but also an engineer, because he managed to invent new devices and even commercialize. Okay, even commercialize it. So became very wealthy by selling telescopes, small telescopes that he didn't invent the telescope. Okay, but he managed to improve it. And the fathers of the city, okay, was so impressed about his discovery that they were very generous towards him. Okay, and let's see, there is something about the pendulum. Let's see the pendulum here. Don't want to talk. We want to talk just about pendulum. Okay, here you go. Here is a scientist. When he returned, he set up two pendulums of equal lengths. Let's see here. Timekeeping. Timekeeping. Let's see. Oh yeah, here you go. Right in here. Right in here. Physics, right? And Galileo claimed that a simple pendulum is isochronous. That is, its swings always take the same amount of time. Okay, let me see. Okay, yeah, here you go. Here is the story. It's popularly believed. Okay, thanks to the biography by Vincenzo Viviani. Who is Vincenzo Viviani? Let's see. Biography of Vincenzo Viviani. He was a disciple of Galileo. Vincenzo Viviani was an Italian mathematician and scientist. He was a pupil of Torricelli and disciple of Galileo Galilei. Okay, so that this began by watching. Okay, the work of Galileo on the motion of bodies began by watching the swings of a bronze chandelier in the Cathedral of Pisa, using his pulse as a timer. Okay, he didn't have a good timekeeping device, so at that time, what he had to do, he had to use his pulse as a timekeeping device. Think about that, in order to use your heartbeat as a timekeeping device, you must be steady. Okay, you must be resting. Make sure your heartbeat doesn't vary as time goes by, right? So just by comparing the vibration, the oscillations of this chandelier with using his heartbeats as a timer, as a timekeeping device, he came to the conclusion that the pendulum, that motion of the chandelier was isochronous. Okay, what means isochronous? Isochronous is something that always takes the same amount of time to oscillate independently of the amplitude of oscillation. So if you have a pendulum, right? You displace it 10 degrees and let it oscillate back and forth, it's going to have a period of oscillation. You displace it 45 degrees and let it move again back and forth, it's going to take the same amount of time. That's what isochronous means. He came up with this, and he was pretty close to reality. Not exactly, but he was pretty close to reality. In fact, this is only approximately true, okay? As was discovered by Christian Huygens, another guy. a Dutch mathematician, physicist, engineer, and astronomer, and inventor too, okay? Galileo also found that the square period varies directly with the length of the pendulum, okay? Galileo's son Vincenzo sketched a clock based on his father's theory in 1642. The clock was never built, and because of the large swings required by the verge escapement, verge escapement is a device, okay? That's the type of device here that we're talking about, would have been a poor timekeeper. So that's, we have something else. Let me see if I can find the simple harmonic motion here. There's a, the story goes that Galileo started building this pendulum. Okay, let's see if we have here. No, it is not this one here. Let's go to Christian Huygens. Christian Huygens has a better timekeeping. Christian Huygens. Okay, here you go. Christian Huygens is here. Okay. If we go to Christian Huygens, let's see here. Mathematics. He corresponded widely with the intellect of his friends. Oh, Christian Huygens was friend of Galileo Galilei. Okay. And the story goes that Galileo Galilei started building his clocks together with his son, but he didn't manage to do that. Well, he needed the help of his son, right? And because he was blind at that time, and he was at the end of his life. And then they advanced in building the clock based on the pendulum motion. And he died. His son continued his work, tried to build a timekeeping device based on simple harmonic motion or pendular motion as well. And he died too. The son of Galileo died at a young age. And Christian Huygens took over this challenge. Okay. And let's take a look here. Timekeeping. Yeah, here you go. Pendulum clock. Right in here. In 1657, inspired by earlier research into pendulums as a regulating mechanism, Huygens invented the pendulum clock, which was a breakthrough in timekeeping. Okay, that was no minor invention whatsoever. The timekeeping device based on pendulum motions was a breakthrough. Why it was a breakthrough? Well, there are very good reasons for that, because it allowed it to make very accurate timekeeping measurements. It became the most accurate timekeeper for almost 300 years until the 1930s. Think about that. You invent something back in the 1600s, and it remains the most accurate timekeeping device for 300 years. Okay, that's how important this invention was. And the pendulum clock was much more accurate than the existing verge and foliot clocks. That's the verge and foliot clocks here. Okay, and it was immediately popular, quickly spreading over Europe. Not only, it was more accurate, but it was very simple also to build some very accurate devices. So this idea was hidden for a long time, right? He contracted the construction of his clock designed as Solomon Coster in The Hague. Have you heard of The Hague, the city of The Hague? Okay, who built the clock. However, Huygens did not make much money from his invention. Pierre Séguier refused him for any French rights, while Simon Duod, okay, he tried to patent, right? In Rotterdam, and on the copy his design in 1658. The oldest known Huygens style pendulum clock is dated 1657 and can be seen at the Museum of Verheyen in Leiden. Okay, so this type of device was 60 times more precise than existing mechanical device, and all it was based on simple harmonic motion. Okay, and that's what we are going to talk about. So that's just a little historic introduction to the importance of simple harmonic motion. Okay, here you go. Here's a very simple pendulum, a device that can be used as an element of a timekeeping system. Okay, is a mass suspended by a string, and you let it oscillate. That's the simplest type of pendulum that you can have out there. And this device, oscillates back and forth in simple harmonic motion. We're going to cover that in detail, okay? So here you go. Those are the forces acting on the mass. The only two forces that we have is going to be the weight and the tension. The speed is very slow. Because the speed is very low, the air resistance is going to be negligible, okay? Here's the length of the pendulum. A similar device is this one that you see here. Not that it's similar as a physical construct, right? In its physical construction. In its physical construction, it's very different than what you see here. Here is a mass attached to a string. Here is a mass attached to a spring, right? Isn't that funny that a string and a spring has very similar sounds, right? Here, is the best example of simple harmonic motion. You have a mass attached to a spring, and when you take this mass off the equilibrium position, at this point here, it's in equilibrium position. The force that the spring applies to the mass is zero. But if you take the mass out of the equilibrium position, the spring starts applying a force to the mass. Okay? You move it further and further away, right? You move further and further away from the equilibrium position, and the force increases. If you played with springs, you'd recognize that, okay? So the moment that you release this mass from this position, the mass is going to start accelerating, in this case, to the left. Okay, at this point in time here, the force that the spring is applying is the highest one. And then the mass is going to accelerate, will continue accelerating, but then the acceleration is going to decrease. There's a reason for that. It's going to pass through the equilibrium position. At this equilibrium position, the force that the spring applies to the mass is going to be zero, but because the mass has some inertia, has some velocity, okay, it's going to overshoot the equilibrium position and is going to move to the other side of the axis, okay? Until the maximum possible position that he can move. Here I'm assuming that there is no friction whatsoever, okay? And the mass is going to be moving back and forth around this position of equilibrium, okay? But let's talk about the physics of this type of motion, okay? The first thing that you have to know, here you go. The first thing you have to know about the the simplest type of simple harmonic motion is that one provided by the force by the force applied by a spring. Okay, if you connect a mass to a spring and put it over a frictionless surface. If you connect a mass to a spring, put it over frictionless and put over a frictionless force, and put it over frictionless force, if the force the spring applies to the mass is zero, then the mass will be at its position of equilibrium. Okay, position of equilibrium, net force is going to be equal to zero. And I am assuming that there is no friction whatsoever. So that what we have here, net force equal to 0. You know, this position here where the mass is called the position of equilibrium. However, okay? However, if you displace the mass from this position of equilibrium, the spring will apply, you know, let's see, if you displace the mass from this position of equilibrium, from its position of equilibrium, at the position x naught, okay, the spring will apply a force that we call an elastic force given by Hooke's law. Okay, and what's Hooke's law? You gotta remember that, I believe I covered that here before, right? Here we go. I'm gonna put the force in terms of vectors, okay? So okay, and I'm gonna put elastic, EL for elastic force, okay? Minus K X hat, okay? Note that we have this negative sign. This is a vectorial formula, okay? Another way of writing this equation is by considering the x not to be a scalar, but being a vector, okay? That's another way to write the same equation. Can you understand that? So the more deformance you apply to the spring, the greater the force becomes, okay? The higher, so the above equation states that the larger the deformation of the spring, the higher, the greater, right? Not the higher, the greater, the force it applies, okay? So that's exactly what those drawings here review, right? Here you go. Take a look. Force, the elastic force is 0 because the mass is at a position of equilibrium. If you stretch, if you apply an external force, here you go. Here's the force of my hand being applied to the mass, okay? An external force. The spring is going to start applying a force opposite to the position of displacement, okay? Okay, so here you go. X is going to be, I'm going to do the following. I'm going to put a little ghost mass here, okay? Here you go. So you can compare what's going on here. Let's do like that. Here you go. See that there is a little bit of a displacement, right, from the position of equilibrium. I'm going to erase that. That doesn't look good. Okay. So the vector position of the mass is going to be this one right here. That's the vector position. You displace it even more, what happens to the force of the spring or the elastic force is going to become greater, right? So here you go. Now we have a larger displacement from the equilibrium position. Here you go. Oops. Take this one out of here. We have a larger force. Yeah. Here you go. It's not. Let's see if I can get it. Man, so difficult. Let's see here. A little bit more. Yeah. X naught. Okay. Remember, is the position from equilibrium. Notice that this force, again, is directly proportional to the distance from equilibrium. The larger the magnitude of this vector here, the larger the force. But don't forget, the force is going to be, is going to have a direction that's negative compared to the position of the object. If a mass is subject to this type of force, it will undergo a simple harmonic motion, okay? If a mass is subjected to this type of force, the object will undergo simple harmonic motion, okay? But let me tell you something else too that I didn't tell you. Here you already know that's the position of the mass with respect to the equilibrium position. But what about this K, okay? In the above formula, comma, K is a constant that depends on the properties of the spring, okay? We call it the elastic constant. The elastic constant. For a given spring, K will always be the same, okay? Its unit is Newton per meter, the unit of K. Oops. Because the unit of K, Newton per meter, like that. Now let's keep on moving here. You gotta have this picture in your mind about the motion of the mass, right? Here you go. The mass is moving now. It's gonna be accelerated to the left, right? When it passes the position of equilibrium, the force applied to the mass is 0, but not the velocity, because the mass has some inertia. It started moving. Okay? And then when it passed to the other side of the position of equilibrium, the force inverts direction as well as the acceleration. Right? The spring is completely compressed here, as far as it can be compressed, and then you make the mass oscillate in the other direction. Okay, that's how it works. You know, let's see. Let me put that the ideal spring. So that equation that you saw is the equation for the ideal spring, Hooke's law. Okay, this force here increases as you displace the spring from its position of equilibrium. What you have here is very similar to what I put there in my drawings, right? At this position, here's the position of equilibrium of the spring. I stretch the spring, I take it out from the position of equilibrium, and that is this force that the spring is applying on the hand of this guy, right? It's opposite to the force that the hand is applying. When you compress the spring is going to apply a force away from to the right. Okay, so that's the equation of an ideal spring, Kx. K is a spring constant. Okay, and I'm going to skip this part here. Here you go. Here, see Kx with the minus sign. You had plus sign in there, plus Kx, because it was the external applied force. But here's the force that the spring is applying to to the object, whatever object it is. Okay. See, that's the unstrained lengths of the spring, the position X, right? The position X is with respect to the unstrained lengths of the spring. If the unstrained length of the spring is this one right in here, any amount of displacement from this position of equilibrium will result in a elastic force. Okay, and if we put this object to oscillate back and forth, you know, we are going to have simple harmonic motion. We attach this object to a pen, and we have this paper here moving with a given velocity. It's going to draw this sinusoidal function in the paper. Okay. 29. Okay, we have something similar here for the vertical direction. Okay, we have something here similar. I also have a drawing here. Let me see if I have it here. Oh yeah, right in here. Okay, so we, let's see here. Okay, we start with this one. That's what we have to start. Okay, we go ahead and attach a spring to the ceiling of a room, right? Provided I don't have any mass attached here to the end of the spring is going to stay at this position that I call it the position of equilibrium. But when I attach a mass to the end, okay, this mass is going to exert a force on the spring, that's the weight of the spring, and will displace the position of equilibrium by an amount y. That's going to be given by mg divided by k, okay? This amount mg divided by k becomes my new position of equilibrium. Okay, if I don't do anything, if I just apply the mass in there, let the spring normally be stretched, and if I don't do anything, the particle is going to remain at this position of equilibrium. It's not going to oscillate, but it's going to be a new position of equilibrium. A new position of equilibrium. Right? Here you go. That's the old position of equilibrium, right? And that's the new position of equilibrium that I put as 0 prime. See, the old position of equilibrium I put at 0, the new position of equilibrium I put at 0 prime. And I can go ahead and write it down here. It's going to be mg divided by k. Right? Mg divided by k. And now I displace the mass from this other position of equilibrium, and the mass is going to be oscillating back and forth, okay? Will be oscillating back and forth. I'm not going to mess with what's coming here next, because it's a little bit more complicated and we haven't covered this material yet. But you can also have the same mass submerged in a liquid, okay? Well, we're not going to cover that, okay, because it's a little bit more complicated. Let's see if I have anything else. No. Here you go. Yeah. Yeah, no, I don't. That's all I have here. Okay, so you can have, so the idea here is the following. You may have simple harmonic motion in the horizontal, bows in the horizontal, bows along the horizontal, and vertical directions. Okay. And that's what we have here. And now, there is a close relationship between simple harmonic motion and circular motion. There is a close relationship here. Let's write that down here. Since you have already studied circular motion, there is a close relationship between simple harmonic motion and uniform circular motion. Even though the former is 1D motion and the latter is 2D motion. Let me explain that. And I have it right in here. Here you go, circular motion. Imagine your sphere undergoing uniform circular motion here in the circle, okay? Constant velocity, right? And what I mean by zero, I mean this position here, the X position is zero, okay? That's what I mean. So, and superimpose the circle to your mass that's subjected to the simple harmonic motion. You go ahead, project a light, a beam of light over a particle that, let me draw the particle here for you, that's undergoing this uniform circular motion, okay? And the projection of the shadow of this particle on a screen right in here is going to move like in uniform circular motion, in simple harmonic motion, up, back and forth, okay? So that's the relationship between simple harmonic motion and uniform circular motion. There's a close relationship between SHM and uniform circular motion, even though the form is 1D and the later is 1D motion and the latter is 2D motion. Okay? The variation of the X coordinate of the equation, not the variation, the equation, okay, of the X position of the particle undergoing uniform circular motion is the equation of motion for a particle undergoing SHM, okay? That's the relationship between one and the other. So here you go, I'm gonna put this particle right in here. And on the top of that, I'm gonna come up with the vector position of this particle. Remember we did that before. We have an angle theta right in here. Oh. You go. Like that. Black color. And we go ahead and put my angle theta. Remember we did that before. No. Oops. Okay. Symbol. the coordinates is going to be given by what? You go. The x coordinate under uniform circular motion, the position along the x-axis of a particle is going to be given by, well, that equation that you already know, right? Here you go. X equal, let's say, to an amplitude, which can be the radius of the circle, times the angle theta, right? Like that. Which, by the way, is going to be given by a constant that I call it omega. And then later on, I'm going to times the time t, okay? That's the very equation of simple harmonic motion, an amplitude times a cosine of omega t as time goes by. So that's what this, that's the equation of this particle here, going back and forth. The amplitude is going to be my x naught in this case, okay? For the mass attached to the spring, for the illustrated mass, for the mass attached to this, for the illustrated mass attached to the spring, the above equation can be written as, go, x naught cosine of omega t. And this one here, x naught cosine of omega t. Okay. See here, the particle undergoing circular motion, right? And then you illuminate the particle with those lights. And as the particle undergoes this uniform circular motion, it's going to, you're going to have a projection of its shadow, you know, tracing this sinusoidal curve in a paper, in a screen that's moving, right? So that is the relationship between uniform circular motion and circular motion. Okay. The distance from the zero amplitude, the time period between this zero amplitude and the next zero amplitude is going to be the period of oscillation of the particle. Okay. So here go. A particle obeying, yeah, this, a particle with this equation of motion will have a period of oscillation that we call capital T. Okay, so here you go. What's the period of oscillation? You just here's the point of equilibrium, right? We release the particle, it undergoes, it passes through the position of equilibrium, okay, overshoots it, and then goes back to the initial position. That the amount of time that it took for the part to complete the full oscillation here is the period. Let me show you again the simulation that I have here, right? Here you go. Let's see, this one here. Okay, it's gonna be here. You know, release the particle, start your timer. You know, when the particle goes back to that initial position, you stop your timer, and that's gonna be your period of oscillation. Okay. And then Okay, this, okay, so how does the period of oscillation relates to this omega factor that I put there in my equation, right? There's a relationship between those two, okay? There's a relationship that between those two, okay? So I can go ahead and here you go. For a full period of oscillation, you know, T equal to T plus capital T, we have the following relation, right? For a full period of oscillation, we have the following relation. The position of the particle time T equal to T, lowercase t is going to be equal to this equation when we sum a period capital T. That's the relationship we have. Okay, for something like that to hold, right? For something like that to hold, we must have what? We must have that there must be a relation between omega t and omega t plus capital T. Let me go. This relation is going to be something like that. Omega t plus 2 pi is going to be equal to that. Okay, and now we can find out how capital T relates to omega. I'm going to expand this term. Okay, omega t on the left side is going to cancel out with omega t on the other side, right? And look what we get. We get that capital T, or the period of oscillation, is going to be equal to 2 pi divided by omega. By omega. Here you go. And now the key here is to find out what this omega is all about. Okay, 9:46 right now. Any questions so far? Did you get a good, let's say, conceptual idea what simple harmonic motion is? That's the idea here today, is to get a conceptual idea of simple harmonic is, and then start working, you start understanding the math behind that as well. Okay, so in summary, let's summarize. You know, simple harmonic motion, by the way, in 1D, one dimensional simple harmonic motion, 1D simple harmonic motion is going to be given by this equation right in here. We also have the period of oscillation is given by this equation right in here. There is more that we can do, but let's we're going to continue that after the break. Okay, let me take attendance first. And Jade, are you there, Jade?
Here.
Thank you. Vanessa, are you there, Vanessa? Thank you. See here. Okay, participants. Okay, Vanessa is here. Ashley, are you there, Ashley? I see Ashley here in my list. I don't hear from her. I'm gonna put a star here.
I'm here. Sorry.
Okay. One. Next is Fisher. Dawn.
Here.
Thank you, Fisher. Blessing. Are you there, Blessing? I don't see Blessing here. Janet Garcia.
Here.
Thank you, Janet. Raymond Garcia. Thank you, Raymond. Lily Hasid. Okay, next is Michael Hasid. Okay, thank you, Michael. Joshua Jimenez. I don't see Joshua. Okay, next is Basilio Lopez. Are you there, Basilio? Good, thank you. Basilio Vahag. Mart, are you there, Vahag? I don't hear you, Vahag. I'm going to put a star here in your next to your name. Days Mariscal. Are you there, David? Doesn't look like she's there. Next is Alejandra Marmolejo. I don't see Alejandra either. Amarilis.
Here.
Thank you, Amarilis. Yesenia Montes Rodriguez. Thank you, Yesenia. Mary Okiki.
Here, Professor.
Thank you. Okay, Vahag also answered me. Thank you, Mary. Ryan Ong.
I'm here, Professor.
Thank you, Arthur Pacheco. Arthur, good. Thank you, Arthur. Jennifer Pettis. Thank you, Jennifer Lebilud. I see Lebilud here, but I don't hear from her. So let me put it here. Donia, are you there, Donia?
Here.
Thank you. Elika Vafe.
Here.
Next is Brianna Valencia. Hi, Brianna, I cannot hear you. If you can hear me, just type there in the chat window. Gonna put a star here next to your name. Mia, are you there, Mia?
Here, Professor.
Thank you. Next, Justina Youssef. Justina is not here. Let's see, 20, 21, 22. Okay, so I have more. Okay, 20, let's see here. Let's see, 20. Okay, so it's 9:52 right now. Brianna, are you there? One more chance here. Brianna and Lebilud. Oh yeah, here you go. Lebilud, thank you. Okay, it's 9:52 right now. Let's go for our break. It's break till, let's put 10, let's see, 10:03 p.m. Okay, and I'll see you soon in almost 5 minutes, a little bit more than 5 minutes. Okay. Okay, we're back here and let's continue. Here is our now. Okay, at this point in time. Okay, we have this relationship between T omega, but we still do not know what T is, what omega is. And since we do not know what omega is, we do not know what T is either, okay? But at least I have made a case in which the position of the particle varies in time according to a cosine function, which is very similar to that relation that we got for uniform circular motion, right? So now let's see. Let us figure out how, omega, right? Omega is also called the angular velocity. How omega is related to non-parameters, okay? In order to do that, we gotta find out equations that we can use to determine that. Okay, one of them is, Newton's second law of motion, right? Newton's second law of motion states that F net is equal to mass times acceleration. But we also know that the net force applied to my particle is equal to minus kx, which must be equal to that acceleration there. Okay. So we do know that x is x naught cosine omega naught, omega t. And what else? We also know from uniform circular motion that this A here, is going to be in terms of cosine of omega t as well, right? So here we go. Let's see here. Let's take a look here. A omega. In the case of the acceleration, right? What we are going to have? We are going to have that the amplitude, that the acceleration is going to be the amplitude of the motion times this omega square, just like we saw before. Okay, so here we're going to be x naught, which is the amplitude of motion, times omega square, and we still have a negative sign here. Okay. Ideally, we should be doing like that. Here you go. I'm going to put the A between parentheses, and now I'm going to put the negative sign here. So you know that this expression that goes here in between parentheses is the acceleration. Right? And then it's just a matter of rearranging the equation to find out what is the relationship between omega and the other parameters that we have. Okay, so here goes. This negative cancel the negatives. X naught cancels with x naught. Cosine of omega t cancels cosine of omega t. And look what we get. We get an expression for omega in terms of the mass of the particle and the constant of the spring, stiffness constant of the spring. Here we go ahead and write down my omega here. And put the square root there. And bingo, that's what we get. Okay. Well, so let's summarize here, right? Summarize here. Simple harmonic motion is closely, the equations of simple harmonic motion is closely related to the equations of uniform circular motion. In uniform circular motion, we have, x equal to what? X equal to the radius. I'm gonna put the radius of the circle, right? And then we also had what? Vt over r, remember that? Vt over r. For the case of uniform circular motion, we have x equal to x naught cosine omega t. For the velocity, we're going to have v equal to v of t, right? V naught or v tangential dt over r. And for the case of a uniform circular motion, we are going to have, not cosine, but sine with a negative sign, right? And we are going to have our omega here as well, like that. And finally, for acceleration, we are going to have, a v naught square over r cosine, that must be a negative sign here. Okay, and this one, a uniform circular motion, is going to be where omega is equal to the square root of k over m. Okay, so that's what we have here. Here you go. Maximum acceleration is going to be this one. There is a relation between, well, in addition to the period, we also have a parameter that we call the frequency of oscillation, f. Okay? If t is how long it takes for the object to undergo a complete oscillation, f is how many oscillations we have in a single second. Okay, so f is nothing but the inverse of t. Okay, and there is a relationship between f and omega as well. Okay, and omega is going to be, 2 pi f, like that. That's what we have here, the frequency of vibration. That's omega that we derived, and we have this example right in here. What we have here is the case of how you measure your mass in space, okay? Using this, those relations that we found out, okay? If you're here on Earth, all you gotta do is to step on the scale, and the weight, the gravitational attraction, right? You have weight here on Earth, is going, we can use the weight, the gravitational attraction, to measure your mass. But there in zero gravity, you do not have a weight because you're floating, you're in zero gravity. You still have mass, but not weight. So it wouldn't work to use a regular scale to get your mass there in zero gravity. So what do? they put the astronaut, right, the test subject, in a chair that undergoes simple harmonic motion. That's how they do it, okay? That's the way to measure the mass of an individual there on space, okay? Astronauts who spend a long time in orbit measure their body masses as part of their health maintenance program. On Earth, it's simple to measure body weight with a scale and convert it to mass using the magnitude g of the acceleration due to gravity, right? However, this procedure doesn't work in orbit because both the scale and the astronauts are in free fall and cannot press against each other. The scale would measure a weight that's going to be equal to 0. Instead, astronauts use a body mass measurement device. The device consists of a spring-mounted chair in which the astronaut sits. The chair is then started oscillating in simple harmonic motion. The period of motion is measured electronically and is automatically converted to the value of astronaut mass. Okay. So we got this guy here, right? This guy here is also equal to 2 pi over t, right? You go ahead, the astronaut measure the period of oscillation, one single period of oscillation. That's your, the K constant of the spring that you send there to orbit, because you made measurement of K constant there on Earth, and then you solve this equation for the mass. We can do something like that. I'm going to square both sides of the equation. Oops. 4 and t squared. We solve for the mass. Here we go. T squared goes upstairs. 4 pi squared goes downstairs. That's how we get, that's how that device calculates the mass, right? The spring using one of the device has a constant 606 Newton per meter, and the mass of the chair is 12 kilograms. Okay, the mass of the chair also affects that, right? So we can, we can put here mass of the astronaut plus mass of the chair, okay? Mass of the chair. So what we end up having here is the mass of the astronaut plus the mass of the chair. Unless the mass of the chair is negligible. Unless the mass of the chair is negligible. Okay, it's 2.5, the mass of the astronaut, right? So here we go. Oh, the same equation that we used here. Okay, and then we end up getting the mass of the astronaut. Okay, here we go. Okay, so if I'm going to mass of the astronaut, this factor here goes to the right side, KT squared, and then you do the mass, you get the mass of the astronaut. Really huge full four. This is the name of the astronaut that was there in the space shuttle long time ago. When was that? They don't say when was that. Yeah, it was back in the 90s when she was flying in space. Okay, she was a researcher there in Boston, and I met the guys that were working with this mission that she flew. Okay, they were doing some life science experiments in the space shuttle together with this woman. They were collaborating with her. Angular frequency of vibration, here we go. Now that's what we have for sections 10.1 and 10.2, okay? We're going to do that now, 10.3. We can also use energy in simple harmonic motion to solve problems, okay? Oops, let's get this thing out of here. Good. And how do you do that? Okay, just remember that, going back here, energy in simple harmonic motion. Simple harmonic motion. Recall, right, that mechanical energy is equal to what? Is equal to the kinetic energy plus potential energy. Okay? And you've got to remember that too, that kinetic energy is half mv squared. And potential energy in this case is going to be the potential energy of the spring itself, right? Remember that the potential energy of the wave is mg, and the potential energy of the spring that we saw before is going to be half kx squared. Okay? In order, if mechanical energy is conserved, right? Initial mechanical energy must be equal to I somehow got this thing in red color here. Let me see if I can fix that. Let me see, it's still red. Yeah, it's still red. Oh man. That shouldn't be difficult to fix. Oh, I know why. Okay, now we got it. Nope, not yet. Let's see. Oh, whoa. I gotta do something else. Sorry, folks. Track changes here. No markup. For everyone, just mine. Let's see. Do not show mark. Yeah, no markup. Okay, now I must have to fix it. Let's see if I fixed it. Yeah, now I fixed it. Okay, E naught equal to final mechanical energy. Okay. So initial velocity plus initial position, right? Initial kinetic energy plus initial potential energy must be equal to final kinetic energy, final potential energy. Like that. Okay, the half can go away because they're common terms. Go away, go away, go, and we have this relationship here. Okay. What else? What else can we do? Here you go. This. Let's just work on this equation here. Okay. And let's write down the velocity and the positions. Let's see what happens. You know, velocity you saw before. It's going to be x naught times omega, right? Sine omega t. Omega t. And here, oh, don't forget, let's not forget that, you know, this thing is between parentheses. And don't forget also that we have a negative sign here, right? Remember that? You go. V. Here. Here's supposed to be a negative as well. Okay, here you go. Negative. And you have a sign. All right, let's not forget that we still have a square. And here we are going, I'm going to copy this guy here because I'm going to use some of it. Okay, we do not have omega, and here it's going to be cosine, like that. And let's see what happens. What happened to the mechanical energy, right? Okay, this guy here is going to be, the negative sign is going to disappear. X naught becomes X naught square, omega becomes omega square. And the sign, oh. And the sign is going to be, strange. Supposed to raise it. Let me check it. This one here. Okay. For some reason, just not doing with my sign. Okay, now we got it. I don't need that. I don't need that square anymore because I already have squared it, right? And I'm going to do the same here for this guy. Okay, let's see if he's going to accept my, well, just copy this one. I'm not going to mess up with that and change the sine to cosine. Okay. Here you go. What else? There's one more thing, very interesting result. Okay, I'm going to put the halving evidence, right? I can put the X naught square in evidence because I have X naught square on both terms, both here and here, right? So, and what is not the common term is those two. Those two are not the common term, right? This and this. Oh, this and this. They are not common term. Let's put in evidence what is common term, and you're going to see an interesting result that you're going to get. Some of those hidden relationships that we have in physics. X naught is no longer here, right? Then, oh, wait a minute. Am I forgetting something? No, that's okay. Now, remember that there is a relationship between K, omega, omega, K, and M. Remember that? Let's go back here, right in here. Right? We have even a better relationship. Where is it? This one right in here. Right? Let's see. Let's try to use this relationship, see if we get something nicer. We can write that down, omega squared being K over M, right? So let's replace it there. K over M. And look what happens. Something unexpected. M cancel out with M, right? And we end up with the same factor here, multiplying the sine and the cosine. Because of that, we can take out the K. We can put the K in evidence here, right? And then, what else? What else we end up getting? We get this relationship between sine and cosine that we know it's 1. Okay? 1. And here you go. We find that the mechanical energy is equal to half kx naught squared, which kind of it seems surprising, but it shouldn't be surprising, right? Because when the object is at a maximum amplitude, its instantaneous velocity is going to be 0, right? And at this very moment, its kinetic energy is going to be 0 too, right? And the only energy that we have is potential energy, which is going to be given by half kx naught squared. So the mechanical energy is conserved. Mechanical energy is conserved is conserved under simple harmonic motion. Okay. What else do we want to do here? Here you go. Energy. So we have some other examples here that we can make. Okay, and let's see. Oh, okay, let's do the pendulum now. Pendulum is important. Okay, a pendulum is just that object that you saw initially, right in here. Okay, a mass attached to a string and subjected to these forces here, weight and tension. Okay. So let's let's break down, this force here, the tension is perpendicular to the motion, right? To the arc. So it doesn't add any energy to the system whatsoever. So here you go. So doesn't add any energy and no torque either, right? The only torque that we have here in the system is due to this force that can apply it in this tangential direction to the mass. Okay, if this angle is theta, this angle here is also going to be theta. So for a simple harmonic, for a pendulum, the case of a simple pendulum, we can steady its motion by looking at the net torque applied to it. Right? So the net torque applied to our pendulum is going to be given by what? We go tau mg, right? But wait a minute, the torque that the pendulum is applying is applying to the torque that the weight is applying to the pendulum, is going to be a function of the cosine of theta, right? Take a look here at my drawing. We have an angle theta right in here. We have this force that's going to be perpendicular to the arm of the pendulum. The arm of the pendulum is L. So consequently, force times the length of the pendulum, it's going to be, hey, wait a minute, sorry, it's not cosine. It's not cosine, right? Let's see, is that cosine or not? Here you go. Yeah, it's sine, right? This one angle is theta. Let me get that for you. Here you go. So you can see more clearly. Here you go. Angle theta right in here. So since we have angle theta here, we are also going to have an angle theta here by extension, right? It started raining here. Okay, if I get disconnected because the light went out, don't but the light comes back pretty quickly here. So don't go away if we're disconnected. Because I will return soon, even if I have to return with my own cell phone. Okay, here you go. So the force component that is applying a torque to this mass is going to be mg sine of theta, not cosine, right? Mg sine of theta. Okay, and that's going to be the only torque that's going to act in my pendulum. Okay, that's what we have here. Oh, there is one more thing. This torque is in the clockwise direction. Consequently, we must have a negative sign here. But then there is a little difference between this equation and mine. Okay. Okay, for small angles, there is this important relationship. There is this important approximation. And by the way, I can prove that to you. Given by, it's easy to see that. So approximately here you go. Yep, approximately theta. And now we have this approximation for the, it's a pretty good approximation, okay? It's not, this approximation is good up to 45 degrees. Okay, this approximation that we see above, you see above is good up to 45 degrees of angle. And we can do that, I can prove that to you in Excel. Okay, that was MGL theta, okay? What else do you have here? Okay. What you see right in here, you know, can be here written. Let me see here. I'm gonna put, I'm gonna here write that. No, you know, I'm gonna put the theta right in here. That's better. All right. Okay. Don't forget that net torque is also equal to I times alpha. Remember that? For a rigid body. In this case of this rigid body, I is going to be mr squared, ml squared. Okay. ml squared, because it's a point particle. Remember the moment of inertia of a point particle is ml squared. Okay, in your book, let's follow the way that the book does that. Now compare this relation here. Let me put that here. And by the way, don't forget, I'm going to put approximate here as well. Here is approximate. What you have there is a angular force, right? Recall that we also have a similar relation for a linear force, which is mass times acceleration, okay? See here, we have linear position, we have angular position. Here we have a measure of the linear inertia, a measure of the angular inertia of our system. Here we have linear acceleration, and here we have angular acceleration. So what you see right in here is very similar to what we see right in here, even though the equations are different. So we can state that what you see here at this spot is a so-called, what their book called, right? The K prime Okay, that's what your book did here. He meant MGL. Okay. Not only that. Okay, not only that, but if you write the angular acceleration in terms of the I, okay, okay, we can equate this ratio that you see here to what? To the omega. Okay, mgl over I with a square root there. Okay, here is my k prime divided by linear inertia, right? Angular inertia, right? Recall, right? Recall that for the linear case, that omega is what? Remember, if the light goes off here, just stay online and I will come back to you very soon, even if I have to use my cell phone, okay? So here you go, that's the linear case, right? But for the angular case, what we're gonna have is gonna be by k prime divided by I, okay? My k prime, man, that's a big storm out there. MGL divided by I. That's how he got that. But let's not forget that my I is also ML squared. Oops, ML squared. Okay, and here we go. M cancels with M, L cancels with L. And that's what we get for the omega for a simple pendulum. Let's not forget that this guy is 2 pi over big T, right? And we can get the period of our simple pendulum as being, big T. Let's see here. L over G, right? Yeah, let's see here. Yeah, okay, T goes here. 2 pi goes here. Okay, that's gonna be 1. And then we can solve for 2 pi. Well, I have 2 pi there at the beginning, right? But that's okay. And then the square root gets inverted when we pass to the other side. L over G. Right? T. Here you go. That's the period of a simple pendulum. L square root. And that's what we have for, let's see, yeah. We're going to stop here at 10.4. I'm not going to cover more than that. And you don't have to worry about 10.5, 10.6, 10.7, and 10.8, okay? So it's 10:45 right now. Let's see. Let's see if we can do another example. No. If we're going to write, okay, if we're going to write the equations here for our simple pendulum, right? It's going to be, let's see here. Let's get the The first one at the top, right, is going to be the circular motion. This is going to be simple harmonic motion. Now, if you're going to add another equation for the pendulum, we put a theta here. That's going to be a theta naught cosine of omega t, but now the omega is going to be different, right? The omega is going to be square root of G over L. Whereas here is square root of K over M. Okay. Here, something similar. Watch out, watch out. Okay, we can, let me see. I'm going to put delta theta. I'm going to put omega prime here so you don't mix up with the other one, the other omega. Okay, omega prime is the angular velocity. And that's going to be, okay, that's going to be something like that. That theta naught is the initial angle of oscillation. Okay, those are the equations of motion for a uniform circular motion, a simple harmonic motion, mass attached to a spring, and here for a simple pendulum. And we must have a negative sign here too. But first, don't forget about the sign, right? And finally, the angular acceleration, alpha. That's going to be G over L. Okay, if you're not confident about those equations, you can start doing some dimensional analysis, right? Here is radians, here is meters per second square, here is just meters. The meter per second square here, the meter in this one here cancel out the meter here. So you get 1 divided by second square, and then you get radian per second square, which is exactly the unit for angular acceleration. Okay, so you can go ahead and insert our table. Let's see, 1, 2, 3, 4, right? Let's see, can we do this way? No, maybe it's gonna be better to do this way. Let's see here. Let's see how I'm gonna do that. Let's start this way and take a look. I'm gonna put in a table format so you can have a better picture of what is going on, right? Yeah, UCM. Here it's gonna be UCM. Gonna be here simple harmonic motion. Here goes simple pendulum. Oh yeah, and then you go. Tables are really nice because if a table is well done, of course, right? Position. Yeah, position, velocity, acceleration. Yeah. So I'm going to put all those equations here in table format. UCM is for uniform circular motion, right? Here you go, acceleration. Here you go. I'm gonna expand this guy a little bit. This one goes right in here. I gotta put K over M. I didn't do that. Square root. Okay, and then angular acceleration. I'm gonna put angular acceleration for you. Whereas the others are linear acceleration, this one is angular acceleration. If you want to have the linear acceleration, all you have to do is multiply that by L, okay? If you want to change that for linear acceleration, here you go, let's put linear acceleration. So you get everything in the same, multiply my alpha by L, and then you get the linear acceleration for the pendulum. So we did for the acceleration. Let's do that for the velocity now. Okay, here's the same thing, right? We can come up with the linear velocity. In order to come up with the linear velocity, we have to multiply the angular velocity by L, right? The L, when it goes inside the square root, becomes L squared. The L squared cancels with the L. We get something like that. Okay, and we have this other linear velocity here for the simple harmonic motion. We have the linear velocity for uniform circular motion. Let's squeeze this guy a little bit more. Okay, and position. What about the position? Here you go. X. Okay, and then we have this theta. To come up with the, not the position, but the path, right? The path length S. What we have to do is to multiply by L and become theta naught L. Blessings coming. 10:54. With light still didn't go off. Okay, we're being lucky. Again, if light goes off, we stay in there. I'm gonna get at least with my cell phone here. But the light here, doesn't take too long to return. Position. Let's go get this thing here. So simple pendulum. This one, good. So I got everything. Did I get it right here? Alpha, yeah, I got it right. I multiply alpha by L and I get the tangential acceleration. Let's call it tangential acceleration. This one is not tangential acceleration, and let's call this one tangential velocity. Just to, and this one is going to be arc length. Okay. 10:55. And that's, let's write it down in our sections. 10.1, 10.2, 10.3, and 10.4. That's what we have for this chapter. Last one is about the pendulum, one of the most important inventions, right? For timekeeping, for timekeeping devices. And we can stop here and I'll go for go for a break, right? It's 10:56 right now. Let's go back. Break from 10:56 to, let's see, 10:50, 10:05 to 11:04. 11:04 now. It's what? 11:11, right? Let's stretch to 11:15, right? Let's just make it seem simpler. Any questions? Let's see here, good. This one, yeah. Okay, if you don't have any questions, let's go for our break, and I'll see you in roughly 15 minutes. Till then, hang in there. Okay, thunderstorm here stopped. So we didn't have any light outage whatsoever. But just in case, I have here my cell phone here as a backup in case that we lose electricity, okay? So let's see here. Okay, good. We're recording here. So we're done with this chapter 10. Okay, 10.1, 10.2, 10.3, and 10.4. Everything else, you know, is more advanced stuff. I consider more advanced stuff that we usually teach at a calculus-based level courses, physics course. What I want to do is go for chapter 11. Okay, and chapter 11, we're not going to cover everything. We're going to cover 11.1, 11.2, 11.3, 11.4, and 11.6. Okay, so it's going to be fluid statics. We're not going to do fluid dynamics. Okay, so let's go just go to my notes here, chapter 11, fluids. That's the type of thing that you need whenever you are dealing with water at home, right? When you have to, whenever you have to install, you know, water devices at home, whenever you put your boiler there at home to pump water from the boiler, for instance, to your shower, you have to know how fluids behaves, how water behaves, to come up with a good system that's not going to break down or that's not going to give you any troubles. Okay, and I just installed a system for heating water with solar panels here, not the photovoltaic panels. Okay, the photovoltaic panels generate electricity, but you can also use the panels just to directly warm water, right? The water goes through this panel, and the panel collects the sun rays, turn the sun rays into heat, and the heat is transferred to the water. In order for you to design a good system like that, you have to understand the basic principles that we're going to teach here in this chapter, okay? And I was learning from this guy that was doing the installation here at home. It was really nice. You know, I was learning things that I never imagined existed. You know, I have this guy that deals with those systems, and they do kind of grunt work, okay? They kind of do grunt work because they have to break things, they have to cut tubes and install it. And he was doing everything here in my house, here in Brazil. I put there a nice solar solar panels there upstairs in the ceiling, right? And that thing warms water like crazy, you know, it works very well. I have seen the water reaching temperatures on the order of 140 Fahrenheit. 140 Fahrenheit, something like that. Okay, it's you know, works pretty well, especially that I'm here in Brazil, right, where which is a tropical country, and the weather here is warmer. We have sun most of the time, and the sun is stronger because it's lower latitudes. It works pretty well. So the funny thing here about in Brazil is that you know, one of those amazing things. I think Brazil is the only country that does that in the whole world. Okay, what we have here in Brazil in general, we install an electric shower. Okay, an electric shower. The water goes to this electric shower, and there is a little cavity there in the electric shower with a wiring that warms up the water on the spot. Okay, it's people when I tell that to people there in the States, they tell me that doesn't thing doesn't that thing get electrocuted? You don't get electrocuted by mixing electricity with water in a single device while you are having shower. No, we don't get electrocuted at all. But the device is very fragile. I learned that the device is very fragile. This electric shower was invented here in Brazil, and most of the population here in Brazil, most of the people buy those electric showers, which are very fragile and they get burned out very easily. So I didn't want those electric showers anymore. So instead, I installed this boiler that pumps, that's connected to a solar panel that warms the water and pumps the water to my shower that's no longer electric, but just the regular shower that we have there in the States, right? That doesn't warm water at all. And it's working pretty well. And then in the next few months, I'm going to install photovoltaic cells here as well and stop paying electricity to the utilities here at home. But why did I start talking about that? Because of the behavior of fluids, right? Whenever fluids goes through those solar panels that warm the water, you have to know what we are going to discuss right here in this chapter. So going back here we go. The first thing that you have to know about this chapter is the concept of mass density. Okay, that's the first concept, that's first idea. Most of you are already familiar with this idea, but I'm going to review it. First thing that you have to know, about this chapter is the concept or idea of mass density, or just density. We call it just density, or just density. Okay. We use this symbol, the Greek symbol, the Greek letter rho, to denote density. And density is defined as what? The amount of mass divided by the volume that a given substance holds. Okay? And if the substance is made of a given material, no matter what's the volume or the mass of that material, the density is always going to be the same, provided you have that pure material in different forms and shapes and masses. Okay, so different substances have different densities. Right, the SI unit for density is the kilogram per cubic meter, right? So we don't, oops. Most likely you have already learned about this thing in chemistry. But let's just review that here, right? Go, volume. Okay. Kilogram per cubic meter. That's the SI unit of density. So different substances have different densities. The standard for density is the water. Okay, and the density of water, we can make a table to list all sorts of different densities. You don't have to memorize all of them, but there are a few of them that you have to know by heart, like the density of water, which is not difficult to memorize. Let's see here, the density of water, here you go, is 1,000 kilograms per cubic meter. But it's water of 4 degrees C. Okay, at different temperature is going to have slightly different densities. 1,000 kilograms per cubic meter is 1 gram per cubic centimeter. Okay, so let's do a little table here. I'm going to do that right in here. Density of water, right? Density. Different, we're gonna, kilogram per cubic meter. instead of writing down density, I'm going to put just the symbol rho here. Here you go. Now we got it. And don't forget to raise this to the cube, right? No, I don't want, I want just to, here you go. Subscript, I don't want subscript. I want superscript. Here you go. Here you go. And then you can also have the density in grams per cubic centimeter. Here you go, cubic centimeter. In the case of water, I'm not gonna put the temperature there. It's gonna be 1,000 kilograms per cubic centimeter. Here it's gonna be 1 gram per cubic centimeter. There's a way to change from this to that, okay? It's not difficult. It's not difficult to do that. All you have to do is to memorize that 1 kilogram has 1,000 grams and 1 meter has 100 centimeters, right? I'm gonna do the math for you only once here. So you learn how to do those conversions, right? How to change 1,000 kilograms per cubic meter into grams per cubic centimeter, right? So consider, you know, the density of water, right? Density of water in kilograms per cubic meter is going to be 1,000. And by the way, water is very heavy. Don't underestimate how heavy water is. It's not light. Okay, one cubic meter of water, which is not a lot. Okay, 1 cubic meter would be like something like that, right? This wide, this tall, and this thick is 1,000 kilograms. 1,000 kilograms is the weight of is the mass of your car. Okay. So here you go. If you want to change that to cubic centimeter, grams per cubic centimeter, all you have to do is to change this unit here. Kilograms. 1 kilogram is what? Is 1,000 grams, right? 1 kilogram is 1,000 grams. And then 1 meter is how many centimeters? Is 100 centimeters. So you put that 100 centimeters, and let's not forget that is the meter that's raised to the cube. Not just the centimeter. Okay, so when we are going to raise to the cube, we have to raise all that 100 centimeters in there. Make sense? So when I do this mathematical calculation, I am going to get 1 gram per cubic centimeter. Let's see if that's true. We have 1,000 multiplied by 1,000, right? 1,000 multiplied by 1,000 become 1,000,000. And I'm going to put in scientific notation. 1,000,000 is 10 to the 6. Okay. Here we are going to have 100 raised to the cube and centimeter raised to the cube as well. And I no longer need that cube outside the parentheses. Okay. You know, but 100 raised to the cube is in reality 10 raised to the 6th power. All right. Is 10 squared times 10 squared times 10 squared. And look, didn't we get 1, like I mentioned to you? 10 to the 6 cancel out with 10 to the 6. And whatever goes here in front is going to be the number 1. So 1,000 kilograms per cubic meter corresponds to 1 gram per cubic centimeter. That's for water. And I can write that down right here. But then we have other substances as well, okay? For instance, solids, right? Like aluminum is 2,700 kilograms per cubic meter or 2.7 grams per cubic centimeter. Brass is 8,400, concrete is 2,200, copper is 8,800, almost 8,900. Gold is very dense, 19,300. Lead, you know, it also is very dense. Quartz and so on, right? Those wood has a density that's lower than the density of water. Okay, Compare the density of wood with the density of water. It's less. It's half the density of water. That's why wood floats on water. Okay, because its density is lower than the density of water. What about liquids? Blood. Blood at 33 degrees C, 1060 is a little bit more than water, right? Blood has lots of water. Ethyl alcohol, 806. Mercury, liquid mercury, very dense. It's a very dense substance, 13,600. Okay, it's more than lead, more than silver, but less than gold. It's it's a very unique substance, liquid mercury. It's a very unique substance. It's more than aluminum, more than brass, more than concrete, right? Oil, hydraulic oil, 800 is less than water. So if you mix water with oil, oil is going to float. You're going to see that layer of oil on the top of the water. And then we have for gases, air. Look at the density of air. Only 1.29 kilograms per cubic centimeter. It's almost one, right? Almost one. Carbon dioxide, helium, hydrogen, nitrogen, oxygen. Unless otherwise noted, densities are given at 0 degrees C and 1 atmospheric pressure. Okay, that's very important. The density of the water, of air, is 1.29, but under those conditions, at 0 degrees C and 1 atmospheric pressure. If you are a higher atmospheric pressure, okay, and 0 degrees C temperature, then the density of air is going to be more, greater. The more you compress air, the denser it becomes, okay? Carbon dioxide too is approximately 2 carbon dioxide. But if you increase the pressure of carbon dioxide, it's going to be more than that, and so on. Okay, so there's a little table of densities. You have to memorize this density. That's not difficult to memorize. And you have to remember that density of mercury is pretty high. Even liquid mercury, okay? It's pretty high. It's a very dense material. Okay, so that's what you have to know first. What else you have to know? Okay. Pressure, okay, you have to know the idea of pressure. Let's talk about the idea of pressure. It's a little bit more complex than the idea of density, okay? Pressure, okay? Okay, pressure, strictly speaking, that's how we define pressure, okay? So you can understand it, what exactly it is. Strictly speaking, pressure is the amount of force per area. Okay? I'm going to give you an example, an illustration. Here you go. I'm going to illustrate pressure here in this slide of mine. Okay, here you go. I'm going to put let's see, yeah, I'm going to use this line right here. Okay, that's the surface of a table. And I'm going to put a block here over the surface of this table. Okay, this block has, I'm going to put something like that. Here you go. So let's say this block has an area of 1 square foot. A surface area of 1 square meter, not foot, but 1 square meter. That's yeah, a little bit high, but that's okay. Okay, now subscript, superscript, yeah? And it has a mass, area. a mass of 10 kilograms. Okay. Let's say here is the surface area, here is 1 square meter. And this area here, the surface area here on this side, because it's smaller, it's going to be just half square meter, right? Can you picture that? A parallelepiped. Ideally, I should be drawing it like a three-dimensional figure. Let me see if I have my, okay, this one here. Yeah, it should be something like that, okay? That would be better. Here you go. This area here is 1 square meter. This other one here is, here you go. Now you have a better picture, right? A better drawing. Here you go. This area. Now the question is, what is the pressure that this object exerts on this surface? Okay, and I'm gonna, again, to make it look like a surface, right? A two-dimensional surface, like that, right? Oh. Here you go. Here you go. That's the surface. The question is, what's going to be the pressure that this block exerts over this surface? Okay. Well, we gotta use the definition of pressure. Okay, so here you go. Pressure is force divided by area. In the case of my block of 10 kilograms, right? 10 kilograms block. Yeah. My 10 kilograms block, the force that's going to exert is going to be, 10 kilograms times the acceleration of gravity, which is 10 meters per second square. Make sense? mg, right? Let's put mg. Divide by area. My m is 10 kilograms. My g is 10 meters per second square. And my area is 1 meter square. Like that. If we go ahead and do this math, we get what? 100 kilograms meters per second square divided by square meter. Kilogram meter per second square is what? Is Newton. Okay. Newton per meter square is the unit of pressure. Okay, 1 Newton per meter square is the unit of pressure. That is the Pascal. Pascal we abbreviate by the letter PA. Okay, that's the picture that you have to have about pressure. But this pressure here that you see right in here is not the same for every orientation of your block. Okay, if your block were to be oriented in a different way, like this way, in this case the area is going to be less, right? What would happen to the pressure? see if I can get it the other way. And yeah, it doesn't have to help. Let's leave like that. The 1 square meter area is this one here. This one is half square meter, right? Now we have a smaller area for the same force. Same force that's being bring to the front. Yeah, this guy is still there. So it's the same mass over a different area, right? A different orientation. Here you go, this guy becomes 100 Pascal. If you orient your mass differently, the pressure is going to be different as well. Half the area, half the contact area, twice the pressure, right? So here you go. Now, instead of 1 square meter, it's going to be half a square meter. And instead of 100 Pascal, it's going to have 200 Pascal. Okay? The same idea can be extended not just to solids, but can also be extended to liquids and to gases. Okay? The same idea of pressure, can be extended to liquids and gases. And it's not difficult to visualize that. Let me try to picture that for you. Okay, think about, we are here on the surface of the Earth, right? Here you go. In this Earth, we are surrounded by this vast ocean, not of water, but this vast ocean of oxygen and nitrogen. Okay, and I'm going to draw it for you. Here goes our atmosphere. We're surrounded by our atmosphere. Let me see. Let me put it smaller. Yeah, here you go. I'm going to make this guy dashed so you know it refers to the atmosphere of the Earth. Can you picture that? It's a much thinner layer than what I'm picturing here, okay? I'm exaggerating the layer of our atmosphere, but it's much thinner than that. Okay, so what do we have to know? You have to know that at a given spot here, let's say we are right here, there's a spot, right? On the surface of the Earth. Right here, there's a spot on the surface of the Earth. We are subjected to this huge column of air. This column of air, let's say, is 100 kilometers high. Can you picture that? At this very moment, we have this huge amount of air that's over our heads. Okay? It is as though we'll be carrying a great deal of weight along the way as we walk around. Okay, and I'm gonna put dashed one here so you know it at first, like this one. Yeah, let's put this one here, like that. Okay, amount of air that weight over our. So if you get the mass of this column of air, which is approximately 100 kilometers high, multiply by the acceleration of gravity and divide by the contact area that you have over your body, you're going to find what is the pressure that this column of air exerts on you. Okay. The same idea, okay? Same idea of pressure can be extended to liquids and gases. For the case of gases, for instance, we can picture this huge column of air exerting a large weight over your head. From measurements, we do know that near sea level, this pressure is said to be 1 atmosphere, which, by the way, is another unit of pressure. 1 atmosphere is roughly 101 kilopascal, 101,000 pascal. Let me make sure is that the right number. It's not much different than what I put in there. Atmospheric pressure, okay? Atmospheric pressure. Let's see here. That's another way of measuring atmospheric pressure in centimeters. Okay, here you go. 101,325 pascal. Okay, 101,325 pascal. If you don't want to bother about all those small numbers, you can just say, it's approximately 100,000 pascal, approximately. If you come up with this value, you are only 1.3% off the accepted value. Can you memorize that easily? It's easy to memorize, right? It's easy to memorize 100 kilopascal, right? 100,000 pascals. It's not difficult, right? So that's the weight that we carry around whenever you move over the surface. Is the weight, is the pressure due to the oxygen and to the nitrogen, mostly nitrogen and oxygen, right? Because it's 75% nitrogen, 25% oxygen, and then we have a small percentage of other gases as well. That's the idea that you have to have about pressure. But there's one more important detail. The pressure due to gases is this funny thing that exerts a force in every possible direction, and not just in the vertical direction. Okay, so if you are a test subject here on the Earth, the pressure that you feel is not just at the top of your head, but the pressure that you feel due to this air, to this ocean of air, it's something that is applied not just to the top, but is applied in a direction that is perpendicular to the surface. Okay, here at the top you have pressure in this direction, but here on the side the pressure is going to be sideways because it's got to be perpendicular to the surface. It's got to be normal, not just perpendicular, but normal to the surface. Okay, so that's the funny thing about pressure. Even though we use the definition of the weight of the column of air, the reality is that this force, this pressure force that is exerted on us is not just in the vertical direction, but it's also in the horizontal direction. And every possible direction that's perpendicular, that's normal to the surface, to a given surface. Can you picture that? Okay. And that's where we come to talk about pressure due to a submerged object. Here you go. Let's talk about that, right? Oh, here you go. I already have some of it. Here's my container, my vessel, that I fill it with water. Okay? Don't forget that at the surface of the water, you have this column of air that's exerting a pressure of 1 atmosphere here, or 100,000 Pascal, 101,325 Pascal. Okay? So here you go. I am representing this pressure as those black arrows. And to the back, here you go. Yeah, here you go. 1 atmosphere, approximately, you know, I want to put it approximately 100,000 newtons per square meter, 100 kilonewtons per square meter, 100 kilopascal. But what if you are submerged? What if you have an object below, submerged under the water here at this point? Okay, can we find out what's going to be the pressure due to the water alone? Okay, here you go. It's like calculating the amount of mass that's above your head, multiplied by G, and dividing by this contact area that we have here. Okay, and we can do that at height H. Let's do that. We can, you know, it's easy to do that. It's not difficult at all. Let me show you how we do that mathematically. Okay, find, you know, I'm going to propose here a problem. Find the pressure due to a column of water that has a height H. Okay, solution is going to be like that. Don't forget, pressure is force divided by area, right? And this force is going to be the weight of this column of water that's above you. But let's not forget that the weight, the mass of the water can also be here written as rho times volume. Can you picture that? One of those funny things about physics and math, okay? If we define the right thing, we can do some pretty amazing calculations and derivations, okay? So what we have here is a cylinder, is a column, is a cylinder of water that's above you. The cylinder has area A. Let me see if I can get my cylinder here as well, so you have a more realistic drawing illustration. Here you go. Here's my cylinder of water. Oh, here you go. Cylinder of water. The cylinder of water has area A and cross-sectional area A and height H. Make sense? So the volume that you see here is in reality the volume of that cylinder of air. So I'm going to here write that as being H times A. And by the way, this A that you see here is the same A that's in contact with the tip of your head. Okay? It's the same A. Okay, and because of that, the A that we still do not know what the value is cancels out. And look what we get. We get something very simple. We get that the pressure due to the water is going to be the density of the water times the height of that column of water times the acceleration of gravity. And by the way, I'm going to simplify that. Oops, I'm going to simplify that. You know that the density of water is 1,000 kilograms per cubic meter. You also know that acceleration of gravity is approximately 10 meters per second square. And let's not forget, I'm going to put an approximation here, even though it's approximation. This is a very good approximation. Remember, we're talking about good approximations here, not any type of approximation. And look what we end up getting. We end up, getting 10 to the 4th power here. Okay. Kilogram meter per second square. See that? Kilogram meter per second square. You recognize that, right? Height divided by meter. 10,000 H newtons per cubic meter. Right? Here you go. I don't like that. I want this one here. Okay, now it's better. And what else? What else can we do? Note that for every 10 meters below the surface of the water, we have an increase of 100,000 Pascal, right? Or for H equal to 10 meters, we have what? 100,000 Pascal. 10 meters here. I'm gonna erase it here. This meter cancel out this other meter. 3 more minutes to go. Okay. This cubic meter becomes the square meter. 10 to the 4 combined with this other 10 and give 10 to the 5th, which is approximately, 1 atmosphere. Approximately 1 atmosphere, or 100,000 Pascal. Isn't that neat? For every 10 meters that we go below the water, we increase the pressure by 1 atmosphere, by 100,000 Pascal. Easy to memorize, right? So if you are 10 meters below the water, if you dive 10 meters below the water, here you go, let's say that's 10 meters below the water, not only are you going to be subjected to this atmospheric pressure of 100,000 Pascal, but you're also going to be subject to this pressure due to the water, another 100,000 Pascal, which is going to be 200,000 Pascal. Okay? 11:58 right now. This what we are doing here again. We did mass density, we did pressure, and now we're doing pressure and depth in a static fluid. That's what we're doing. It's a fluid that's not moving, but it's a fluid that is at rest. If the fluid start moving, then we have another type of pressure there that we call room pressure. Okay, but we're not going to cover room pressure. What we're going to do, we're going to stay in static fluids. We're going to cover, we're going to 1, 2, 3. We're going to cover 11.6. A little bit of pressure gauge too, but pressure gauges is, there's nothing much to tell you. Pressure gauges is just how we measure pressure. Okay. We're going to skip Pascal principle and we're going to go straight into Archimedes principle next time. Any questions? Okay, 11:59 a.m. right now. 5 o'clock p.m. here in Brazil. Now that you folks are on daylight saving time, on the regular time, right? Standard time. 5 hours difference. And if you don't have any questions, I see you the day after tomorrow. Okay? So see you on Wednesday.